Hello and welcome to this recording of Finite Element Analysis, talking about loading on your model, and this particular one is on the application of loads. We're going to take a look at an example where we will do some thermal loading, and then we're going to go into a stress analysis and see how we can take those results from the thermal analysis and apply them into our structural analysis. In this particular example, we're going to utilize Inventor Nastran, so we'll go ahead and take a look at the program there now. Here we are inside of Inventor, and we're working with the subassembly that we've been working with. And to pick something off of the model that we're going to focus on, I'm going to focus on this small little subassembly right here. So I've opened up that, and here we can see that we have a couple components. This might be threaded, but for our hypothetical situation, what we're going to say is maybe the assembly of this is going to be a press fit, just as a completely hypothetical example. So we have two ways that we could approach that, right? We could take this shaft and we could cool it down and insert it into this joint and allow it to come back to ambient conditions, or we could heat up the bracket here or joint, and then once it's expanded, move it on top of the shaft. So the way I'm going to do it is with the former approach. So we're going to envision that we can cool the end of this shaft down in a way, and we'll examine that with simulation and see if we're able to get the amount of contraction that we need with the given conditions of what we're able to do. So let's go take a look at the quarter shaft here, and this is the part that will be downloadable for you to explore if you want to give this a shot on your own. And I've made a small change to it. So this is the end which would be pressed in or threaded in. Again, we're going to simulate cooling it down so that we could insert it and then create that interference. What I've done is approximately 12 inches up from the end, I've created a split line here. So whenever we set up our thermal analysis, we're going to say that we're able to put this into something, whether it's a refrigerator or some sort of cooled liquid, and we're able to get the temperature of these surfaces down to, say, 0 degrees Fahrenheit. And then this next region here, we're going to envision is insulated. So maybe that's how we're holding it in the liquid, or we're inserting it into some sort of refrigeration unit. So this is going to be just insulated again. And then at the far end here, these surfaces, this will be exposed to just regular ambient environment. So natural convection. So how can we simulate that? So we basically have three different thermal conditions that we're going to apply here. And with the thermal analysis, we'll see ultimately what our temperature distribution looks like. And then again, we'll go into a structural analysis and see if we get the amount of contraction that we need. So let's go ahead into the simulation environment. From the Environments tab, I'm going to go ahead and select the Autodesk Inventor Nastran. And up to this point, what we have looked at is things in linear static. And in our case, we're going to start with a thermal analysis. So by right-clicking and editing the analysis, we're going to change to linear steady state heat transfer, so we can see what some of the different loads look like in different analysis types. And I'm going to go ahead and say OK. And the next thing I'm going to do is take a look at my idealization. So it brought over the carbon steel. That's what it was set to in Inventor, and we can see that it has properties here, and for the most part I'm happy with this. What I am going to do is set the reference temperature. So I'm going to set the reference temperature to 70 degrees Fahrenheit. So again, that's our reference, which means anything on this model, anywhere on the model where we go below 70, then that's going to cause some sort of contraction. Anything above the 70 degrees, then it should experience some sort of expansion. Okay, so let's go ahead and say OK to that. And the next thing I'm going to do is generate a mesh. So I'm going to go in the mesh settings. And as far as the meshing is concerned, let's say that we set a mesh size of 0.5 inch. and that should be pretty fine. So I don't think that we need to use parabolic. We'll set it to linear, and I do think that should be sufficient. Let's go ahead and say OK, or generate mesh, excuse me, and we'll generate that mesh. Okay, so now our material has been defined, our mesh has been defined, our analysis type has been defined. What we're left with here are defining our loads. And if you remember, we are in a thermal analysis, and this region where I created that split line on down, these are the surfaces that I said somehow we're able to cool these to 0 degrees Fahrenheit. All right, so we can do that in a couple different ways, but for this one, what I'm going to do is go ahead and select these surfaces on the outside of the geometry. Let me zoom in here, select a couple more surfaces. Rotate it around here a little bit. And that surface right there. There we go. Make sure that I have all faces. And we're going to assign a temperature to it. I went kind of quickly there. So from the drop-down menu, again, there's our different loads. And as we come down, we see those ones which primarily apply to the thermal analysis. Your temperature, you can do convection, you can do radiation, heat generation, and heat flux. And we're going to assign a temperature of 0 degrees Fahrenheit. And we'll say OK. All right. And you can see the glyphs or the icons that get added to those surfaces for the temperature. It's going to stick with a cylinder on the end of it. And there we go. All right. And one of the things I should mention is due to symmetry, and this was covered in one of our other courses, one of our other videos, due to symmetry, I've cut away 3/4 of this model, right? Because given what I'm going to do on it, what happens in this quarter of the model should be the same thing that's happening in this quarter, and so on and so forth. So this is really going to give us a couple different benefits. One, by having a smaller model, the whole simulation will go faster. And then the other thing is, when I get to the structural analysis, because I have those planes of symmetry, whenever I apply my symmetry constraints, that'll help stabilize this model without artificially constraining it. And that might make a little bit more sense when we get into the structural analysis. Okay. So then we have this region of the shaft, and I'm going to say that that is insulated. So I don't know. It's a completely hypothetical situation. So maybe if we have something where we can insert this into some insulated container, and inside that container is the environment where it's 0 degrees Fahrenheit. So we insert, this 12 inches of it, and then maybe this goes through the wall of the insulated container. And then these surfaces out here, these are the ones that are exposed to the ambient conditions. So those surfaces there, we're going to go ahead and select those, and we'll apply something there that might simulate ambient conditions. So let's go back into loads, and we'll start to select our entities. That would be this surface here, there, just selecting everything. I think I just took an edge. That's okay. I'll show you how to deal with that. And just starting to select everything that I can in that region as far as surfaces are concerned. And then maybe I want to rotate the geometry around. Right there. There we go. Looking pretty good. And of course I'm not selecting the symmetry planes, right? Because those in the whirl world are where other material exists. So that's just, conduction. Whatever I apply on the outside of the model, conduction would drive the temperature or pull the temperature into or away from that. So I don't need to do anything there. So that looks good. I think I selected all the surfaces that I want there. Okay. So when I was picking those surfaces, just doing a quick double check to make sure I have what I want. One of the things that I did was I accidentally selected a edge of my geometry. So just scrolling through the list here, I can find where that is. So there's the edge. So I want to select that one and delete that edge because I just want to apply the loads to the faces. So what I'm going to do here from the pull down menu on loads, we're going to set that to be a convection, right? So these are exposed to the environment, so it's just convecting, just a natural convection. And we're going to say that the room that it's in or environment that it's exposed to is 70 degrees Fahrenheit. And then we need to assign what our convection coefficient is. So I'm going to use a convection coefficient of about 0.01. You can look up what some natural convection values are for flat plates and vertical plates and so on and so forth. But I'm just going to choose about 0.01, which really should drive that surface to ambient temperature. And from there, we'll go ahead and say OK. And that will apply the convections to those faces. So there we go. This, again, this end of the model is exposed to the ambient environmental conditions of 70 degrees Fahrenheit. This end of the model, I'm saying, is stuck into some environment that's forcing the surface to be 0 degrees Fahrenheit. And then the goal of our thermal analysis here is what is the thermal distribution along the length of this thing. And that's sufficient for the setup on the thermal analysis, I think. Let's go ahead and perform the simulation. We'll take a look at the results that we get. Okay, fairly quick. No errors. Okay, and there we can see what we have for our model. Right at the end where the convection was, maybe I should rotate this around a little bit. Let's do that so we can look at it a little bit more cleanly. So at the end where the convection was exposed to 70 degrees Fahrenheit, we can see that we have 70 degrees according to the flag, and our legend here shows 69.999. And then down towards the end of the model where we have this stuck into some sort of refrigerator or coolant, we're holding those surfaces at 0 degrees, and then of course we have to have some sort of gradient between those, right? So we have temperatures around 30 degrees, 35 of course somewhere in the middle of this geometry. So that is what the thermal analysis does for us, and some of the thermal loads that we can apply to the geometry. Now the next portion of this is remember we were cooling this down so that hopefully we can insert it into the hole there so that ultimately we can get some sort of interference fit. So our goal was to figure out how much, by how much this shrinks, right? And then what are the stresses as a result of us, doing this thermal loading on it. So what we're going to do here is return back to the setup environment, and I can right click on my analysis here, and I'm going to say that I want to duplicate the analysis. So when I duplicate the analysis, it gives me analysis 2. We can rename that analysis 2. And I'm going to change the analysis type. I don't want to run a steady state. Now I've already run my steady state heat transfer. What I want to do is run a linear static stress so we can see how it expands and contracts due to those temperatures. So we'll say OK. And when I say OK, it says, hey, you've got some loads on this model which are no longer applicable. We're going to go ahead and remove them. So I'll just say OK. And you can see that it takes off the convections. I don't need the applied temperatures on here any longer either. So I'm going to go ahead and remove those myself. Okay. So let's set up our boundary conditions first. Remember, this is a symmetric model, and given what I have, right, this end is cool, this end is about ambient, so I expect some contraction, but I don't want this whole model just flying around in space. So because this is a symmetry plane right here, the axis perpendicular to it is the z direction, so I'm going to apply z symmetry to this cut plane. So I'm going to go Constraints, and I can go to Symmetry. Actually, It had some faces selected. Let me go back to constraints, and I'm going to go to Z Symmetry, and you can see what it constrains. TZ plus the two out of plane, or the two in plane rotations, RX and RY. So let's go ahead and select that face, and we'll say OK. So that symmetry plane, and maybe I should name it, Z symmetry constrains TZ for me. So that's taking care of that degree of freedom. And I'm just going to give myself a note that that's my Z symmetry constraint. And then if I rotate the model around a little bit here, this is our other cut plane, and the axis perpendicular to that is the Y. So we need a Y symmetry constraint there. So let's go back into constraints, select Y symmetry, select this surface there. All right, and you can see what that's constraining. So that adds my TY constraint to my model. Right, so now somewhere in the model, a linear static stress model needs to be statically stable, right? So now we have Z constraints on that face, we have Y constraints on this face. So down at this end of the model, what I'm going to say is it doesn't matter. Either end face, I could select the faces there and apply an X condition, right? So if I hold this end of the model, X fixed, then everything, if it's all contracting overall, then it'll all move towards that constraint. If I select this face, then everything will move towards or away from that face. So it doesn't really matter in this case which end I take here. So I'm going to go constraints, and I can say free, but then just select TX. There we go. And I'm just going to call that the hold. And we'll say OK. Alright, so we have our constraint set up for this particular analysis. What do we want to do about the loads for it? Well, I could add other loads. If there were things like forces on it I was concerned with and pressures that I was concerned with, I could certainly add those into this model. But in this case, I just want to see what is the reaction to those temperatures that we solved for from our heat transfer analysis. So the way that we grab those temperatures is we go into loads. That brings up my load screen here. And when I go to type, there's an option here that says from output. So that's the one that we're going to set. We're going to say from output, and then I can go browse for my results file. So I'm going to call these incoming temps just as a name, and then I'm going to go browse for the temperature output file. So in my case, the model I had saved in a folder called demo, and you would browse to whatever folder, of course, your model was saved in, and you're starting with a model called quartershaft.ipt, and when you run a simulation, you'll notice it creates this subfolder. Whatever your model name is, it creates a subfolder of the same name. And in that folder, when we go inside there, you'll see another folder that has the InCAD name associated to it. I go inside there, and there's an FEA folder. I go inside there, and then there, the .fno is the output file from my heat transfer analysis. So all I need to do is select that file, say open, and there we go. So now it knows, in this case it's a thermal analysis I did. There was only one subcase, but if there were multiple subcases, you can choose which subcase you want to pull in and then what data you're pulling in. We want to pull in the temperatures that it's able to see in that file. So we can say OK to that. And that's all I need. I have my constraints, and then we again we're going to pull the temperatures from the heat transfer. And then from our material, remember we defined what that reference temperature is of 70 degrees Fahrenheit. So anything cooler than that should cause anything cooler than that should cause a contraction. Any incoming temperatures that are higher than that would cause an expansion. Let's go ahead and run the simulation. See what we get here. And the solution is complete. Nice and quick. And there we can see the stresses. The default result type it comes up with are the solid von Mises stress, and in terms of PSI, really low stresses. So 170 PSI at a max around the boundary between the cooled and the insulated region, so nothing I really need to worry about in terms of stresses for this shaft. Certainly if we saw stresses that were, of course, getting near the yield of the material, we know that we might end up with some sort of permanent deformation or some residual stresses that maybe we don't want as a result of this operation. But in this case, stresses are all good and low. My goal, though, we can see the deformed shape of the geometry. We can see that at the cold end of this shaft it's contracting in. And the question is it contracting enough for what we need to do? So let's take a look at the stresses, take a look at the displacements so that we can inquire on what that is. And I can interrogate either this node here to find out how much it displaced along the y-axis, or I should find the same thing on the node on this axis, how much it contracted in the z direction. Either one of those should work with me. So let's take a look at the, say, along the y-axis. I accidentally chose x. Let's say along y. There we go. Alright, so there's that. And if I find my probe, there we go, access probes, then I can move over top of the geometry, and there we can probe on it, and we find that we have a displacement there of about 0.00058. We'll say 0.005, or again, alternatively, see how much we got there, 0.00055. 0.00055. Right? So this contraction along the y-axis should be the same as the other quarter of this model in the z. Let's check that real quick. Let's go displacement along z-axis, and we'll select that 0.00, again about 0.00055 if I round. So at that point we know that is how much it's contracting in the radial direction, right? Of course, it's a quarter model, so I'm losing, I shouldn't say I'm losing, I'm shrinking 0.00055 inches in half of the model, and then it would be coming in 0.00055 from the other side of the model. So the diametral shrinkage on this model would be 1/1000th of an inch. So the question is, how much interference do you need? Does that give you enough so that we could insert it, and then once it expands back out to ambient conditions, does it give us the interference that we need? Okay, so and the cool thing about this is that's a little bit of example about how to do all these loads and so forth to interrogate things like temperatures, and then looking at a stress analysis. What we should know is that we don't even need we don't really need a finite element analysis program to tell us that, right? Or at least we can check our work. So let's go back to the tools here, and let's go measure. We can measure an edge. So you can see that the length of that edge, remember I inquired this point here, the length on that edge is 1.181. So you could jot that down somewhere. Let's go back to our Nastran environment. 1.181 was our length. Let's pull up our properties here. And let me see if I can get a calculator up here. Should have a calculator right there. So there we go. We know that when we want to calculate the expansion or contraction, I lost my calculator again, that it's a alpha delta T L, right? So there's my alpha right there, 6e minus 6. So let's go 1, 2, 3, 4, 5, 6, 6, 6, 6, 7, a few more decimal places than we need. Times, there's my alpha, the delta t, remember I set the stress-free equal to 70, but then I applied 0 degrees Fahrenheit down there, so my delta t is 70. So there's 70 degrees Fahrenheit. And then the length we just inquired on was 1.181, and by calculation that tells us the shrinkage there should be, or contraction should be 0.00055, which is exactly what the program came up with. So we can even validate that nice simple example there. So again, hopefully how to do that process is pretty clear, and that is something you can utilize. Thanks.